The ones in the exam paper weren't too bad.
Okay, good. Anybody, any questions on
Yeah,
those?
like it's just the mock ones. The exam ones are like doable.
Right, yeah. The mocks do tend to be harder, so don't get too panicked about it. I mean, they're good for doing practice and that.
Yeah,
Don't worry too much about them. And it's, as I say, it's just exposure to different ways they can ask things and twists. But I think the mocks in general aren't thought out as well, and they do tend to be harder. And you tend actually to find mistakes sometimes on them and that as well. So don't worry about it too much. But as I say, it's just to get the exposure. So as many questions as you can is better. What about the questions on the integration? Were they all right? Anybody want me to go through any of those?
Yeah, there was one part of it that I didn't understand, Miss. It was the, I think it was question 3, part 2, where it's asking you for the 2 values of t.
Find the values of t when the body is at rest. So what happens there? Yeah, my camera is not working, so I'm going to have to do the whiteboard thing again. Okay. Okay, don't worry too much about it. You don't need full access to this. But... Okay, so the acceleration is equal to 6t minus 12. Okay, so to get the velocity, we integrate that. So we're doing the integral of 6t minus 12. I'm just going to go through this quickly because I know you can all integrate. So that's 3t squared, 6 over 2, minus 12t plus c. Okay, and we know that velocity is 9 when t is 0. So that's v. So that means c is equal to 9. Okay, so I'm just going to cross that out and put in a 9 there. Is that okay with everyone?
Yeah.
Yeah.
And then the s is the integral of v dt. So that's the integral of our 3t squared minus 12t plus 9 dt. So that's going to be, new thing is 3, divide by 3, so that's t cubed minus 6t squared plus 9t plus c, and they tell us s is 6 when t is 0, so that c becomes a 6. Okay, now if I was doing this out properly, I'd rewrite it out again, 6. Okay, find the values of t when the body is at rest. So when the body is at rest, what does that mean?
When v is equal to 0.
Exactly. So you're basically just solving this. Sorry. Putting this equal to 0. So you've got 3t squared minus 12t plus 9 equals 0. And then divide it all by 3, because just to make the factorizing easier. So that's t squared minus 4t plus 3 equals 0. And then you just factorize that. And that gives you 2 values of t because it's quadratic. Does that make sense now, Joe?
I just substituted in random values, and then I got one of them that was equal to the answer in the back of the book, so I didn't really understand.
No, it's you're solving a quadratic. You're basically saying at rest means v equal to 0, so solve the equation v equal to 0. And so you put in this 3t squared minus 12t plus 9, because that's v, let it equal to 0, and you say, oh, that's quadratic, I need to solve the quadratic. First thing I can do is divide everything by 3 to make it a bit easier. And then that's just a factor. So t equal to 1 or t equal to 3. Sorry, 1 or 3. Okay, does that make sense?
Yeah, I just treated it like it was a function instead of a quadratic.
Okay.
Thanks, Miss.
No problem. So we're going to move on to the next section, which is definite integrals. Let me open up the book here. And I know some of you were in for doing this before the break, but we'll just do it again anyway. So a definite integral, the first thing you want to remember, so the key remember with differentiation, we know that we're getting the slope and we know that we're getting the rate of change. With integration, what we're actually getting is the area. And we'll show how that works now in a minute. Integration is calculating the area under a graph. So if you have a graph and you want to get the area between the graph and the x-axis, when you integrate, that will actually give you the area. And obviously, if you're doing a shape, it has to have a start point and an end point. So just to take that line there, you've got the line y equal to x. So if you integrate x, you get x squared over 2 plus c. Okay. And I'm just going to move over here. I'm going to make that a bit smaller and get the Jamboard up on the right. That a bit smaller. Sorry, just so we can see both of these at the same time. I'm just going to the page here. Okay. And I'm going to do a little experiment here, if you don't mind. I'm going to record this just to see how it works. I haven't done this yet. So do you all consent to join, to be recorded?
Yes.
Yeah.
Yes.
Yes.
Thank you.
Yeah.
Okay.
Yeah.
All right, so it should be recording now. I'll put it up on Google Classroom later, just to see how it works out, if you want to give me any feedback on it. So we can see the book here on the left and the whiteboard on the right. So basically we had our graph of y equal to x. Okay, and we were going from 0 to 3. So your x value here is 3. And if y is equal to x, then that means that's 3. So basically this is a triangle, base 3, height 3. So we know that the area of a triangle is half the base by the height. So half of 3 by 3 is 9 over 2, which is 4.5. That makes sense to everybody?
Yeah.
Okay.
Yeah.
Just to show you that the integration will work. So if I integrate this graph, okay, and I'm integrating x dx, okay, and what I want to do is I'm not integrating the whole line. I'm just starting here and finishing here. So what that means is I have limits to my integration. So where we put the limits is at the beginning, at the bottom of our integral sign, and at the top. So the one at the bottom is where you're going to start integrating, and the one at the top is where you're going to finish integrating. Okay, and these are important, I say, in practical, real life uses of integration where we're actually working out things like area under a graph. So if I integrate x, I get x squared over 2. Yeah. Do that. I have to use the other type of x, it's much easier. X squared over 2 plus c. Okay. Now, when we have limits of it, so you're just doing your integration as normal, but when you have limits, you have to work out the value of this at both of those limits. Okay, so I put the 2 limits in here. Usually we use square brackets. So you just do your integration as normal, and you'll see in a few minutes, we won't actually need to see. And then you put square brackets around it, and you put your limits at the bottom and the top at the end of those brackets. So what you're going to do is work out this when x is equal to 3. So that's 3 squared over 2 plus c. So you take the first, you work out the first one, and if you like, you can put that in brackets. And then you're going to subtract the second one. So that's 0 squared over 2 plus c. So I'm just subbing in 3 for x, working it out. Then I'm subbing in 0 for x and working it out. So this is 9 over 2, so that's your 4.5. And then you have plus c here, minus c here, so the c's cancel. 0 is gone, so we end up with 4.5, which is exactly what we got by working out the area. Okay, So just by using a straight line and the limits, we see that integration does in fact equal the area under the curve, okay? Now, under the curve is just a quicker way to say it. If you notice in the book, it says it's the area between the curve and the x-axis, starting at 0 and finishing at 3, okay? Now, sometimes it'll work, say I wanted to get the area from 2 to 3. So say I wanted to get the area of this shape here. Okay. So now using a formula is a little bit trickier there. We can see it's a rectangle, and that would be 1 high. So that's 1, and this is 2. Okay, so that's 2 for the rectangle, and then there's a triangle on the top, which is 1 by 1, so that's a half. That whole area is 2.5. Okay. Integrating, I'd have the same formula, except now I would have a 2 here. So I'd be doing 3 squared over 2 minus 2 squared over 2, which is 9 over 2 minus 4 over 2, which is 4.5. Does that make sense? I'd have 2 squared over 2 here instead of 0 squared over 2.
Yeah.
So that would be 4 over 2 is 2, and I'd have 4.5 minus 2, which is 2.5, which is the area of that. Okay, so it allows you to get all different shapes and sizes. And obviously, if it's just a straight line, it's easy to use the formula. But if you have a curve, we don't have formulas for getting the area of this kind of shape where it has a curved top. And that's where integration comes in really handy. You just need to know where am I starting and finishing, integrate it, and that'll give you the area. Okay, so that's the key point here, is the area enclosed between the curve, the x-axis. Okay, it was the y-axis we were doing dy here, but it's the x-axis. And the lines x equal to a and x equal to b, they're 2 vertical lines. Okay, so we're doing a vertical line, that's the edges of our shape. So we're starting at a, finishing at b, and that encloses a shape. So that's why it says the area enclosed. Okay, so you've got 4 lines there enclosing it: the curve, the red line, the x-axis, and the 2 vertical lines. So the formula is the integral starting at a, finishing at b of the curve, which is y times dx. Okay, and the nice thing is when we integrate it, you can forget about the constant because it's always going to cancel out. Okay, so you only have to do the actual integration, and you don't need to write in plus c when you're doing it. This is called what we call a definite integral, because it is a definite start and a definite end. So just looking at the notes here, it's called a definite integral because it gives a definite answer. So instead of having an x squared over 2, we actually have a number, because we're going to sub in these numbers. So it gives us a definite number value, and that's why it's called a definite integral. We'll have an actual number answer. If you don't have the limits, it's an indefinite integral because we don't know what the constant c is, and also you've got x squareds in there as well. Okay, the numbers a and b, the top and the bottom, they are called the limits of integration. So it's the limit, it's basically the start and end point, and it's the limits of your shape. It's the vertical limits of your shape. Okay, a is called the lower limit because it goes to the bottom, and b is called the upper limit. And the constant of integration may be ignored, which is great. Okay, highlight here. That's a great thing. Okay, constant of integration can be ignored in definite integrals because they'll cancel out. So for now, we're just going to focus on actually calculating them, and then in the next section we go on to the areas. Okay, so areas will be covered more fully in the next section. So I'm just going to go on to a new frame here. So we're integrating, limits are 0 to 2 of 3x squared dx. So you just do your regular integration. So I would add 1. So I've got 3x cubed over 3. So that's just x cubed. Okay, is that okay with everyone? And then I put my little square brackets around it and say I'm going to work this out at 0 and 2. And it's basically what we say is it's f of b minus f of a. So this is your b. So you work out f of b and you work out f of a. So it's going to be 2 cubed minus 0 cubed, which is just 8 minus 0 is equal to 8. And that's the area under that graph. Okay. Next one is a little bit more complex because it's always nice when the limits to 0 because then you don't have any calculations to do in the second bracket. This one is going from 2 to 4. X squared minus x plus 3 dx. So if I integrate that, I get x cubed over 3. Sorry about the writing. Minus x squared over 2. So plus 3x. And I don't need to worry about my constant. I can just put in the brackets and put in my limits. The lower limit is 2 and the upper limit is 4. And remember, this is f of x, this is f prime of x. So I'm doing f of 4 minus f of 2. So I basically do 4 cubed over 3. Minus 4 squared over 2 plus 3 times 4. That's my first bracket. And then I'm going to subtract the second one. And if I had the camera here, I could show you. You can actually, once you've gone this far, 2 squared over 2 plus 3 times 2. If you write it out like this, you could put it into the calculator exactly like that. Okay, you can have 4 cubed over 3 minus that, put all that in brackets, and then do another set of brackets and put all of those in. Sorry about the handwriting there. Is that okay, guys? Is that?
Yeah, it's grand.
See it here better anyway. So you've got 64 over 3 minus 16. 4 squared is 16 over 2 plus 12. And then in the second bracket, you've subbed in 2. And you can work out that on the calculator, work out that on the calculator, and then do one minus the other. Just be very careful when you work out this one, put it in brackets because you're subtracting, okay? And it's very easy to mix up the signs then, all right? So I would work out this, write it down, work out this, write it down, and then do the subtraction, okay? And then with the second one, or the last one here, we've got 1 over root x. So remember, we don't have a rule for root x. We have to change it to x to the minus a half. And then when you integrate that, you're going to add 1. So it becomes x to the plus a half divided by a half. And when you're dividing by a half, it's the same as multiplying by 2. Remember, keep, change, flip. So if you flip 1 over 2, that becomes 2 over 1. So it's 2 times x to the half, and you can rewrite that as root x. Everyone okay on that?
Yeah.
Yeah.
And then you're doing 2 times the square root of 9 minus 2 times the square root of 4. So that's 2 3s is 6 minus 2 2s is 4, and your answer is 2. Okay, so there's nothing new here except subbing in at the end, and you don't have to worry about a constant integration. And so this is good kind of revision of all the rules for integration. So cos 2x, remember, if we integrate cos, we get sine, and then because there's a number in front, we're going to divide it, because if we were differentiating it, we would multiply by 2, but because we're integrating, we're going to divide by 2. Okay, so that's just revision of that. And then you'll notice, a lot of the time when they do trig functions, they will give the angle in radians. So all you have to do is sub that in, and you can put it into the calculator exactly like that. Sine 2 brackets pi over 2 divided by 2, work that out, and then work this out, and you'll get 0 minus a half, which is minus a half, okay? So you can put it in exactly, you can go straight from here to here, and from this one to the minus a half, okay? Is that all right?
Yeah. I think
Yeah.
Yeah. And then e to the x, you just integrate it, still e to the x. So the 4 can just come outside. That doesn't kind of affect things. It's not part of the x. Okay, so the 4 is a constant. It can just come outside. When you integrate e to the x, you just get e to the x. So we've got 4 times e to the x. You put in your 5 and your 2. And most of the time, you'll notice when you look at exam solutions and everything, you could work that out in the calculator, but they're usually quite happy if you just leave it like in this form. So it's fine to leave it like that. And then a to the x, again, if you look on the log tables on whatever it is, page 30, whatever the page with all the integration rules is on it, you'll see the integral of a to the x is given as, sorry, I'm just flicking through trying to find it here. You see it's a to the x over ln a, which is exactly what they've done here. 9 is equal to a, so you've got 9 to the x over ln 9. You're going to put in a 2 wherever there's an x is, so that's 9 squared over ln 9 minus 9 to the 0 over ln 9. Put them both into the calculator like that, and you'll get your 80 over ln 9, okay? So let's just get you guys practicing these for the next little bit. So let's do 2, 3, 4, and 5 here. Actually, let's do, yeah. Actually, I'm going to do this one because it has a negative in it. So be very careful when there's a negative. Remember to put brackets in when you're subbing it in. And then if we go on to the next page, actually, okay. So scrap 3. Do kind of harder ones. So if with those, if you can do 5 and 6, you can ignore 2 and 3. Okay, it's just to kind of get you warmed up. But if you feel more comfortable doing them, go ahead. I'd rather you did some of these harder ones. So we will do 8. 8, 10, 14, 16, and 17. Okay, we'll leave it at that. So we've got 15 minutes now if you want to get started on them, and then I can jump in if you're stuck. And I'll post it up on Classroom. And I'm going to stop recording now as well. Sure how well that worked out. So let me just hit this button. Oh, okay, this is an issue now. Jamie, you're the host of the meeting. So Jamie, you must have been first here, so it's getting saved automatically to yours. So if I'm recording in future, the best thing is if I'm going to have to host the meeting, I'm going to have to open the meeting first. So I think going forward, guys, you can join the meeting, but as soon as I join, we're all going to have to log off and on again so that I'm the host. So just, I think, be ready to go, but don't join the meeting unless you see that I'm in already. Is that okay? Does that make sense?
Yeah.
Yes.
Yeah, because if we are saving things, it'll only work if I'm the host. Jamie, you can delete that. I'm not too worried about it. Or if you want to share it with me, Jamie, just so I can have a look at it. You can email me the link from your drive or share it from your drive. Okay, so create assignment. I'm just going to start with question 5, but as I say, if you want to do the other ones just to warm up, that's fine. Yeah. What did I say? 8, 10, 12. I have 15, 14 or 15, guys.
Miss Jimmy, tell me to tell you his mic isn't working.
Okay, thanks. You can still hear me okay? Sorry, when I shifted pages there, I lost the ones I had marked. Was it 8, 10, 12, 14 and 17, was that it?
Yeah. I'm not sure.
I will go with those anyway. 8, 10, 12, 14. Just shout if you're getting stuck on anything. Need a hand. I need to take the roll as well. Okay, so I have Aaron. How's your break, Aaron? Okay, I have Andre, Matthew, Sean, yeah, Aaron, Beth missing, accordion, yeah, Andrew, okay, Ben, Reading. Oh, yeah. Okay. Jamie's here, Pavel, Alan, yeah, Dylan, yeah, Andre V, Joe's here, Tyke. You're missing Tyke today? Okay. And Harry was here. Yeah. Okay. Everyone doing okay?
Yep.
Yeah, so good.
Yeah, it's not that it's really much new here, and it's good revision for the integration. And keep that page 26, the tables open in front of you for reference as well. I got that link. Thanks, Jamie. I was left you there. I had marked you absent. Fix that. Okay, lads, I'll let you go unless anybody's anything else you want to ask or.
Hey, miss.
Thank you, Miss.
Thanks,
Yeah,
miss.
Okay.
Thank you.
Thanks, Miss.
All right, take care.